All right, AP Physics 2, what's up? We are on to Unit 3. It's electric potential and electric fields, and I'm going to jump right in because we got a bunch of slides to go over, and I want to make sure we get through them all and take less than an hour here, okay? So we're going to start pretty easy, and like we've done through a lot of parts of this class, we're going to do a little bit of a review of chemistry first. So we'll see how much of this you remember. I'm going to jump right into charged objects. So a charge is an uneven accumulation of protons or electrons. If something has more of one or the other, it's going to have an overall charge. Reminder, protons positive, electrons negative. These are things we probably don't need to say. But the amount of charge is going to be measured in coulombs, and we'll get to this guy named Coulomb here in just a little bit, but that's a buildup of charge there. And you see that one proton and one electron have a very small charge in terms of coulombs overall, and that's because there needs to be a lot of them to build up any kind of real charge. So the better way to think about this, as opposed to saying one proton is this tiny, tiny positive charge and one electron is this tiny, tiny negative charge, is we're going to say a coulomb is made up of this many protons in the positive means, and then a negative coulomb is made up of the same equivalent there of electrons. All right? And these are, as all quantities are, as all constants are, found on your equation sheet. Now, you probably also remember positives, or well, I should say likes, not just positives. So two positives will repel, two negatives will repel, like charges repel each other, and then opposite charges attract. And that's going to be helpful later on here when we start talking about directions of these forces and all of that going on. Because as we know, positive and negative, just direction. Things that hold these charges are known as conductors. And again, we're kind of doing a review here, but these contain free charges. They can move easily. So the electrons, the protons, they move around through the constant here of the object, through the mass a bit easier. It allows flow of electrons to build up, and they're more likely to generate electric fields. And this is because of something known as electrostatic equilibrium. And this is where all free charges can move outward from the conductor, allowing them to really flow more freely. And we see a lot of times they build up, and we see over here, right on the right, they build up a lot around the outside because they can move freely and are drawn to other charges that are nearby. Now, insulators are going to do the opposite, and they're going to keep free charge from moving around. So electrons are going to be held within orbitals of the bonds there, and it's unlikely to allow an electric flow to build up or to hold on to any type of friction. In both these cases, we see some examples, the conductors being mainly metals, the insulators being a wider range of plastic, rubber, ceramic type materials. All right, we see wood and wool on there as well. So we got these charges, they build up, they can be positive, they can be negative, they've got values. It's time to talk about quickly here about how it is that happens, right? So three main methods by which we can build charge. The first one and the most common one, and the one that you've experienced when you grab a door handle when it's cold outside and it shocks you, is charge by friction. So depending on the substances, and this is heavily dependent on the materials that are undergoing friction with each other, but friction between objects, this can create an electric field. So two things rub together, and that happens. And so in the case of a cold environment, so a dry day when electrons are more likely to move freely, you can walk around in shoes with socks on. Maybe you're walking on the carpet in your house. Maybe you're just walking around with your socks rubbing inside of your shoes. But then you reach out and touch something, and the net charge that you've built up through this process, or a charge that you built up on the outside of you, will discharge, and you'll get a little shock there from doing that, right? So we got certain materials. The net charge overall has to equal 0, and that's really important. Conservation is still a thing, and is certainly still going to be something that we need to consider as we do this. And if you were to count them all these little pluses would add up and be the same number as all these little minuses on the other side. So must still be conserved. Charges must be conserved in the same way that mass is conserved, because these charges are just made up of masses anyway. The next means of charging here is known as conduction. And this just means that you put conductors together and a charge will transfer if one item has a charge or more of a charge than the other one does. What you'll end up with is an equilibrium state. And so we see a negative charge here being brought to a conductor. Electrons transfer until we have an equal buildup on both of these objects here through conduction. So we've got two metallic objects, and we've got spreading out essentially of these charges over both of the objects. The last one here is electrostatic induction. This one's a tiny bit more complicated, but let's talk about this real quick. So what we do here is we introduce a charge to a neutral system. So what we've got two metals right here that are right next to each other. And they're metals, they're conductors, they're going to have positives and negatives associated with them. If I bring in a charged item, let's say we've got this balloon in our hand here that's got a negative charge built up because we got friction on it. I don't know if as a kid anybody did this, but if you rub a balloon on your hair, it'll make your hair stand up. That's exactly what's going on. Right here, through friction, we've charged this balloon to have a negative charge overall. As we bring it closer, reminder, in conductors, charges are allowed to move more freely. And so we've got these two metallic objects, and the negative here, all of the positives are going to move towards it. So the positive charge buildup is going to happen over here on A because opposites attract. The negative charge buildup is going to happen over here on B because likes repel. So we have still an overall neutral for this system of A and B together. We have just had the charges move to different parts of the system. Well, once we've done that, we can then move these two objects apart from each other. And so we have now a buildup of negative charge on B and positive charge on A. And we have successfully charged neutral conductors by means of really just spreading out the charge as we do so. All right. Now, around this, and obviously these things are happening here without any contact, right? And so there must be something going on beyond a direct contact or a transfer of a force or a transfer of actual mass here overall. And what we are doing is we're building up what's known as an electrostatic field. So in an electric field here, this is an area in which a non-contact force generated by different charges causes objects to move towards or away from each other. This is and to jump back to this important term, non-contact force. We've really only dealt with one of these so far. And so I'll give you like 2 seconds to think about what it is. And yes, it is gravity. Gravity is the one non-contact force that we've really covered up to this point in physics. Now we will cover another one, and it comes from a metallic object also, and it's known as magnetism. Those are our three big non-contact forces. So gravity down, electric fields coming up, and magnetism to be visited in our future. Now, as you know, anything that has a direction associated with it, we need to make sure we know what the positive and negative is. A field charge for an electric field is considered outwards from the center charge source if it's positive, and we see those vectors pointing out from the positive here, and inwards towards the center charged force if it's negative. So our direction is out from positive and into negative. Okay, that's our positive and negative, just direction, just like always. So when we get two charged objects close to each other, the field that they generate will interact in a way that, again, moves out of the positive and into the negative. And this allows for an overall charged field to be made between two charged objects. So we've got our positive and our negative charge here. We see with electric field lines the general buildup of the charge, and we're gonna, or the strength of the charge, I should say, of the field charge. Apologies. And we're gonna get into this a little bit more later, but in short, the tighter that these electric field lines are to each other, the closer packed they are, the stronger the field's gonna be. And if you look at it, what that's telling us is the closer you get to the charged sources, the stronger the electric field is going to be. And then in between the charged sources is where it's going to be particularly strong. So yeah, that kind of gives an idea of how these things would interact with each other. Now, if we were to put, let's say, another little charged or even a neutral particle in these fields, then they're going to move because of the field, because of the buildup of charge that could be put on there for a neutral particle. Or if a particle has a charge, like let's say if we dropped a little positive charge right in the middle here, right? The positive is going to push it away, and that's what this field line is representing, and the negative is going to pull it in, and that's what this side of the field lines represent. And so if that's going to happen, and those pushes and pulls are going to happen, we define pushes and pulls as forces. And so there are electric forces that are going to be present in this as well. So we need to make sure that we talk about that too, okay? So we're going to have electric forces between, right, the repulsion or the attraction for the opposite charges and the like charges. This is happening also with the electric field, Okay, so there's going to be forces associated with this also, and we will actually have a mass accelerate because of these electric fields that can be present in different spots. The strength of these electric fields is something important to understand for sure. And so we're going to have this capital E here representing our electric field strength, okay? And you see here we've got a constant in one case, and we're going to talk a little more about the variables and the units associated with them and stuff like that. But I want to make sure that you know that there's a couple ways that we can do this. So the strength of the electric field, right, it can be measured of the force between charges and the charge of an individual item within the field are known. So E, electric field strength. F being the force applied within that, and Q being a charged object that it is applied to. Okay? So we're going to have then, for electric field strength, newtons, our unit for force, per Coulomb, C, our charge unit. All right, and we see that right here, newtons per Coulomb. Now, it can also be represented in volts per meter, and we'll get to that a little bit later. And here you see a little bit more in-depth formula here, but this is assuming some different knowns, and we'll get to this coming up here as well. So a couple examples real quick of what some of these different electric fields can, the values associated with them. I think that that's important to know. So some common electric fields right here, and then there's an example at the bottom. You can pause that and run the numbers here real quick if you need to. But if you are near a charged rubber rod, we talked about charging via friction earlier, and the little zap you might be able to get from that. You can see there it's approximately 1 × 10⁻³ newtons per Coulomb. And a TV picture tube, right? The old school TVs, you turn them on and they start to make that kind of crackling noise. That's actually a buildup of an electric field as well. That can get up to 1 × 10⁵ power there in terms of newtons per Coulomb. In order to make an actual spark in the air, you need a little bit greater than that, 3 × 10⁶. But those old tube TVs can build up enough to give you a little shock. But this would be more like the, you reach out, like I mentioned earlier, for the metal doorknob, and it shocks you a little bit. And then an electron orbit and a hydrogen atom, it's going to be much greater than that, so up 5 × 10⁻11. And that's, again, a little more of a chemistry concept, but just to kind of give you a general idea, we're going to be dealing with big numbers is really what it comes down to, right? In the thousands at least, if not significantly beyond that with some of our factors of 10 that are going to be associated with these fields. So that's important to know. So jumping back into the electric force. Right here, I would have potential ways for us to fill in these different ones, but a quick reminder, right? Opposites attract, and so we see our force of attraction. Likes repel. So in the case of this right here, this force right here is working on this object because of the negative charge over here, right? So this object is being pulled to the right because it's got a positive charge and it's interacting with the negative charge, and then vice versa. This force pushing this object outwards is going to be happening because of the charge on the opposite side, and like forces repelling, or like charges, repelling. We will always have Newton's third law applying here, and so you'll see these vectors, same length, purposefully, because these forces are going to be equal and opposite in direction, or, I guess the pairings will always be equal and opposite in direction, regardless of whether they're attracting or repelling. Now, the actual force can be calculated if we know the charges here that are present. And this is done through that guy named Coulomb. So Coulomb's law tells us that the electric force between two charges can be calculated in newtons based on each of the charges, Q1 and Q2. All right, so let's say we have two charged objects right here. We could find the force between them, whether it be attracting if they're the same charge, or repelling if they are, attracting if they are opposite charges, and repelling if they are like charges. If we know the charge value of each of them, and if we know the distance between them. And as always, we will do a little bit more with this equation once we get into class and into these different, sections of this unit. So, quick reminder, charges will be positive or negative, but that only tells you that direction. Keep in mind your direction. That's very important with this. That can get some students on this, all right? That K value that's right there, you see it, it's Coulomb's constant. It is a very big number because we are often dealing with very small numbers for the charges, or large, well, I should say relatively large in comparison to the charges values for the radius. Okay, so we'll have some big numbers, and there'll be a lot of times 10 to the something, and we'll get some practice with that coming up. So quick reminder, just a little bit of a different way of looking at it, because I do like this image at the bottom here and I couldn't fit it on the previous slide. So again, like charges repel, opposite charges attract, Coulomb's law written there one more time. You've got your units for each of these. Make sure your radius is in meters. And I mean, your charge in coulombs is going to be pretty constant. We know for sure by now that force is in newtons, but make sure your radius in between these objects is in meters, and it should be center mass to center mass. Now, that being said, you know, protons and electrons are pretty small, and so the radius of these objects is not very equivalent unless they're very close to each other, or not very important unless they're very close to each other. So, you know, we're not too worried about that. And then the reminder there of our standard charge value. Okay, and so we could calculate these items as well. So I've got an example here real quick. I'm going to have y'all pause it on this one, and I'm just going to hit the solution in a second, but I would go ahead real quick and just run some numbers for us real fast there. Finding the force on the 3 Coulomb charge, find the force on the -4 Coulomb charge, and what if the same charges are moved so that they are 3 meters apart? You've got the charge values there and the locations that they are at. So pause real quick, and then we'll jump into the solution in a sec. 2, 1. All right, so the solution here real quick, we see we put these objects on the number line. We're plugging some numbers in there. And then I say, why is there no calculation for part B? Hopefully we're realizing, again, Newton's third law is telling us equal and opposite forces. And so that's all that really matters. We've just got one acting in a positive direction in the x direction there, right? We see it represented by our number line, our negative value, and then one in the positive direction. And for part C, we've just cut the radius in half and done a similar calculation. So we are rolling already. We're doing pretty well here. I'm going to keep us moving. All right, so that's Coulomb's law. Now, it's important, again, that we realize that conservation is a thing. Conservation is always a thing. Matter is never created or destroyed. We've known this the whole time we've been in this class, and that still needs to hold true. That's going to hold true for electric charge as well, and that correlates directly to conservation of mass, which is really what it all correlates to, because it's these small masses that hold these charges, right? So electric charge is conserved, but that's basically saying protons and electrons also conserved. They are neither created nor destroyed. So we see objects here, right? It's got net charges, and well, we've got some charging by friction here in the middle, and we see the net overall. So now we've gone from 2 pluses and 2 minuses, so 2 protons and 2, well, we'll say 2 equivalent positive charges and 2 equivalent negative charges. Over here, there's 3 of each. We do our charging here via friction, and now I have 2 positive charges and 4 negatives, so a net of -2. And to move my head out of the way here real quick, 3 positives and 1 negative there now, so a net of +2. So since my net total here was 0 and 0, now I have -2 and +2. I still have 0 overall, and so everything is holding true the way that it should be, and we have conservation present. All right. Now, we saw earlier some values here and some equations for how to try to figure out an electric field, but I want to make sure that we realize here we've got that point source, and that was drawn as a 2D drawing earlier with just like the little source in the middle and all the arrows pointing out or in based on the charge of the source in the center. Something I want to make sure that we realize is that this is actually happening in a sphere, in a spherical shape in 3D space. Okay, so it's going to be spherical in shape as you're seeing this right here. And so what we're really going to have is we're going to have the source in the center being the area around which the field is the strongest. And then as you move out, it's going to dissipate. And you see a little bit of that here in this charged object. Now, the electric field strength is going to drop to 0 once we hit the object because it's a non-contact force. As soon as you contact it, we're going to lose that attraction force. And some other things could take over, but we'll cover that in later units. But as you move further away, we're going to decrease exponentially. And you see that curve happening there. And so we see the same electric field equation that we saw earlier, and again, we'll do much more with this, right? That's why it says review here, okay? We saw this earlier, but we are working in the shape of the sphere as well, and so that's helping describe why we're dissipating exponentially and moving outwards, and why you see the 4 pi associated with this as well. So we'll do more with this coming up too, but I want to make sure we realize this is happening in 3D space, not on a flat surface. Now, time to talk about something called a dipole. This is any object with north-south, positive, negative, anything associated with that. What that means is we have 2 or more charges. Dipole typically referring to just 2, but I've got an example here that has more than that because I want to make sure that we see how all of these things could interact with each other, okay? What it really comes down to, oh, it doesn't like my effect. English. Sorry, but we've got an object with a roughly square shape and 4 different charges placed on the corners here overall. What I'm going to want to know is, when we've got any sort of dipole situation, is what would be like the overall force acting on this central charge based on these other charges. So what I'm going to do is say something along the lines of, and we'll see more examples like this coming up, but I would say something along the lines of, okay, charge A and B and C and D, they're stationary. They're there, they can't move, okay? We now introduce a charged object towards the center here. I want to know what happens to that charged object. Now, if the charged object Q in the center is negative, right, and all of these charges around the outside are all positive, and it's exactly in the center, and they're all the exact same charge values, then they're all going to hold it in exactly that spot, because the force between these two will equal the force between those two, and that equals this force, and that equals this force, and so overall our vector sum of forces would turn out to be 0. Now, more likely, we're going to have like 2.2 coulombs here and 4 coulombs there and 1.3 coulombs here and 2.2 coulombs, whatever, something different. And so we would have to use Coulomb's law to determine the force between each one of these, determine the 4 forces acting on this central charge, and then find the net force from there. So prepare yourself. We're going to have some vectors coming up in this unit for sure. Now, instead of having these different point charges, a very practical use of this is to take 2 plates, 2 metal, or we'll say conducting plates, and put them near each other and build up a charge between them. All right. Now, you know this, or have heard of this to some degree, typically referred to as a capacitor, but more commonly referred to incorrectly as a battery, right? This is a buildup of charge between 2 plates, and this is what a rechargeable battery is. And we'll talk about that coming up also. So this is the very introduction to that, but this is how these things hold a charge that is still allowed to flow through your devices and be used to some degree. So we get 2 plates of opposite charges. They're brought close together, and so they generate this field between them. The strength of the field is going to be determined by a couple things, okay? The charges of the plates and the area of the plates. What that means is I got 2 plates near each other. If I have a charge of 1 on each, that's going to have a lower overall field strength in between them as if I have a charge of 10 on each. And if I make one plate bigger and the other plate bigger, I'm going to have a greater surface area as well, and thus a greater overall electric field in the center. The other thing I can do is change how close they are to each other and the separation there and the voltage that's added to them. And we'll talk more about how that different methodology works as well. They will both work for us here to determine the electric field strength in the same way earlier on. For E, we had that difference too. So the charge must be uniform in distribution and charges must be far from the edge of the plates. And what that really means is we want to build this up uniformly, or we're going to have some issues in between here. And we also want to make sure that it's charged in the center and not around the outside, because then we're going to start losing some of what we've built up. The electric field strength, it'll be perpendicular to the plates. So if I have plates like this, the field builds up in between them. And that's what's really important as well. And a charged particle can move through this electric field very similarly to a projectile motion. It's really what it comes down to. We got a non-contact force. It's going to move similarly to an object that we launch, and take a parabolic shape in the same way that gravity causes whatever projectiles we looked at earlier to move in parabolic shapes. So some examples here and what this might look like. Our different field buildup, right? We've got a positive and negative plate, a positive and negative plate, a positive voltage here and a negative voltage there, all saying the same thing. We've got to have these opposite charges. We've got field strength buildup. You see a little bit of why we have some issues if we build up around the outside. We're going to have the field strength be, we want to keep it uniform in order to make it a practical use for this, which again is charging all these objects that we charge. And as we move towards the outside, we're going to have that field strength decrease as it has to move in a longer path. And so that's just not going to be ideal. So we're going to try to, we really care about these areas in the middle here. All right, we see a lot of our equations that we will build on much more later. Charged particle between these plates. So what can happen too then is if I take this particle, any one of these, and we see, so right here we've got our gravity, right? It moves off the edge and it goes down because gravity is always pulling down. Well, here, depending on the charge, it's going to move to one plate or the other. So let's say I've got a negative charge and I've got this buildup of a field in between, and I've got all these positive charges here and negative charges there. A reminder, this negative will repel from this negative, and so it will move this way and it will move towards that positive also. Now, the reason it's not going in a straight line straight towards it is because this is a very small particle that will likely have a very large velocity. And so that will keep it moving through the center here as that initial velocity to some degree, in the same way that this ball rolling off the table here had an initial velocity and kept moving straight. All right, so that's what happens. So we've got that. A quick example of, and for those of you who have taken that fake science class known as biology, you've almost certainly seen this example. You've maybe even done a lab with it. But this thing called gel electrophoresis, believe it or not, it uses parallel plates to grab the charge and cause the separation here in these different particles. So really what you're doing is you're creating a DNA fingerprint, and I'll save you the fake science stuff. You can go take that biology class if you need to. But we have different sized particles that move down through the DNA fingerprint as it forms, and that happens because a charge is driven between these objects, and heavier particles, the force generated from this charge movement moves them less, and thus they stay higher up at the top, and smaller particles are pushed further down. You run this for a certain amount of time, blah, 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 ask your bio teacher. But just thought that's kind of an interesting example of how some of this stuff works. All right, to get into the specifics of how some of these items are calculated and what the reasoning behind doing a lot of this is. So this particle within this field is going to be accelerated because it's moving and it's got forces acting on it, and that force is going to be an electric force. So as is the case between these plates, it thus then generates kinetic energy. Anything moving is going to have kinetic energy, even very, very, very small particles. And the smaller they are, honestly, the more likely they are to move quickly as well. So expect some of these velocities to be pretty high. The presence of this kinetic energy means that the electric field is doing work on the particle. So it was stationary, and now it's doing work. We're going to have a really hard time determining work being done and the kinetic energy potentially of some of this stuff. Oh, potentially, didn't mean to do that, but love it. And so we're going to have a hard time kind of determining some of this. So instead of looking at the actual kinetic energy and trying to like measure, oh, it's moved this far in this amount of time, because this far is going to be almost nothing, and this amount of time is going to be almost nothing. What we're going to do instead is look at the location that it's moving to and from and determine the amount of work that can be done based on the change and potential in those different locations between the plates. That sounds like a lot right now, but here, let's look at a little bit more of that right there, okay? So determining the work in an electric field, it's very difficult. Just said that, right? So a correlation's made between different quantities. Really what we're going to do is we're going to apply what we already know and what's already been mentioned about these electric fields and how they're generated and how the electric fields are made, and our conservation of energy to make some equivalencies to make sure that we can make we'll say an extremely educated guess as to where these particles are. All right, and we won't get into Einstein and so forth and so on, but we don't always know where a lot of these electrons are no matter what. So the different plates each have their own electric potential. We've mentioned that. That's V, electric potential, also known as voltage. And the difference in the electric potential between the plates and the charge of the particle being accelerated are related. So the difference in voltage between the plates is going to be one minus the other. That's going to equal the change in potential of a charge. Okay? So that difference in electric potential is going to equal the change in potential energy, gravitational potential, divided by the charge of the object. This seems crazy right now, but we will elaborate on this quite a bit and keep going there, right? I'm even going to elaborate on a little bit more. Apologies, I forgot I had one more here, right? The thing I do want to make sure to mention is the difference between that electric potential that is voltage and the electric potential energy, PE, because those do sound a lot alike, and we don't want to get those confused. So electric potential energy is the energy it takes to put a charge in a given place. Okay, so the electric potential energy, this is our PE. This is like an object being at a specific location and the same, I'll say very similarly to our gravitational potential energy, right? That's our electric potential energy. Electric potential is that potential energy there that we just talked about, divided by the charge of the individual particle being considered. And that's where we get this equivalent again also, okay? So the electric potential is that voltage V, whereas this electric potential energy is more like the gravitational potential energy. So please try to set those in your minds the right way, because that can certainly get confusing. Now that I've mentioned all this V and all this stuff, I want to make sure we elaborate on that. So V voltage is, or potential difference, is going to be measured in volts and is equal to that electric potential, E in joules, because it's energy in joules, divided by Q in Coulomb. So we see here that this volts are equal to or equivalent to joules divided by coulombs. Now that's based on our standard units, but a reminder that a lot of what we're going to be using is going to be very, very small. So there's actually equivalent microscopic units to help us better explain this, so that we don't have to constantly say this crazy number, 1.6 times 10 to the negative 19 joules. That is what the charge of like I should say one proton because it's positive, or if it was negative 1 electron would be. Instead of saying that, we're going to say it's 1 electron volt. Okay, and we're going to make that equivalency there. Now, I realize, again, this is throwing a whole bunch of units at you, and a lot of things seem a little bit crazy here, but an electron volt is equivalent to one of those standard charges for a proton or an electron. All right. Now, to continue to take a step back there and say, okay, we mentioned this potential, electric potential energy, but we were talking about kinetic and these objects moving, and how do we make this overall correlation? That happens because of conservation of energy. So it holds true for these particles that are accelerated there. The kinetic and that electric potential will be constant throughout there. That electric potential, we said, is QV. And so that's what that potential would be at the beginning before an object is accelerated. Once it is accelerated, then it's going to be that plus the kinetic, which would be 0 with the time, is going to equal then just the kinetic, because the potential has been used, and we're going to have 1/2 mv squared. And so we can have our velocity here being equivalent to the root of 2 times q being the charge of the particle times v being the difference there in voltage between the fields, between the plates, divided by the mass of the object. Looks a little crazy written like this also, but again, we'll do much more with that as we keep going. Really, I'm just saying conservation of energy still holds true. All right. Uniform electric field. I guess I'm just defining, this one seems a little redundant, so apologies, but I just want to make sure that we're defining here that we are going to use this. Oh, that's why I put that in. I'm sorry. Here's specifically why no calculus is required. Because we do this algebraically, this is why we need that uniform electric field, and we're just going to focus on the center areas of these plates as opposed to the outside, because algebra loves straight lines, And that's what we're going to work with. This is AP Physics 2. It is algebra based. So we have to focus on the areas that have a uniform electric field. And we will just focus on these spots here where these arrows are nice and straight between our plates, not where they're curved on the outside, because we would need some calculus to help us determine that. So, yeah, there we go. We are getting close here. Last couple things. So the electric potential due to a point charge. So we've got that V, and this would be if we have like a source somewhere, a point is in space, and we want to determine that potential based on that. That's going to be K Q1 over R1, right? And what that is saying is we have this, let's say, point charge here. We don't have plates again. We have this main charge in the center. I want to know then that electric potential, this V value, based on the point in space around a charge overall. We can calculate that as well. And this kind of brings us back to our spherical shape that we were talking about at the beginning, but leads us into, because we see our equipotential lines there, how a lot of these can interact with each other. So we're back to hitting these a little bit more in depth. Real quickly to wrap us up, lines, these connect points of constant electric potential. So thinking way back up here in the beginning, oh, maybe I can find them. When we first were talking about these interactions, what they're doing is these lines, everything along that line has the same electric potential. Okay, and so that's what it's showing us. Now, in the case of this right here, it's, well, as you move further out, that electric potential changes uniformly, and same thing here. But then we see once they're interacting with each other, we get a little bit of a different ratio based on how close these charges are to each other and so forth and so on. What's important is these equipotential lines, these circular lines. Think of them like lines on a topographic map, all right? Everything along those going to have that same electric potential. They will be perpendicular to the electric field lines because they have to be in order to be of the same value. And so it's going to be based on how close to or far away from the source they are. What we can see with this then is, instead of having this craziness over here where we've got all these arrows moving in and out and everything else, we can find the spaces where we have the same potential, electric potential, and thus we can help determine, right, the work present or that it needs to be determined or applied in order to move between these different lines. We see we've got -5 and -10. We could find the difference in potential between those and determine the work that needs to be done to move an object from, let's say, this -5 V line to this -10 V line. The other thing we can say here is if I move along this -10 V line, no work is required to make that happen because we have the same electric potential all the way through there, and there is no delta V. And that's what I've got for you today. So wrapping it up, we do have a lot we need to build on for this unit, but we will do that as we get into class. So I'll see you as we do that.